Thank you. Thank you for inviting me up. So I will be talking about identification in some very, very simple discrete choice models. And I'll just say up front, this is a little bit of an obsession that I've had for a long time. So there's a big risk that I care a lot more about this than you do, but I'm going to try to convince you that you should care a little bit anyway. I should also say that what I'll talk about is kind of out of some stuff that I have done, is doing, and will do with various co-authors. So as you'll see in a minute, the literature that I want to talk about is really a combination of some very, very simple econometric techniques and econometric models, right? So most of what I talk about is just a simple combination of panel data models kind of at the level of Stock and Watson's chapter 10, and simple binary outcome models at the level of chapter 11 in that book, and simple time series models in chapter 14. So really, really simple stuff. So we really ought to know how to do this, except when we combine them, we really don't. Okay, and so that's kind of what I think makes this interesting, and as an econometrician, why I think hopefully I'll convince you that it's useful, but I also want to convince you that it's really something we should know how to do, because it seems like a simple combination of simple things that we know. Okay, so what I'm going to do is I'm going to first give a very, very selective survey. I should say, I'm kind of in the spirit of Ming Li Chen. I have a very limited number of references. I like all the papers I reference, but I like a lot of other papers. So if I don't reference you, it's not because I don't like your paper. I will talk about so I'll give a little bit of survey, then I'll talk about some new results and some new things that I don't know if they're results or not. So I'm just going to describe them as puzzles or things that I don't understand. So you'll see what I mean by that. And then at the end, I will try to convince you that this kind of literature is useful even if you don't care about any of the econometrics that I'm talking about. That the insights that I'll be talking about, you can actually use in other contexts. And I'll talk a little bit about an empirical example that I'm working on and try to convince you of that. Okay, so, all right. So, the big picture is that I'm interested in panel data, right? And we know if you have a linear panel data model, you can allow for fixed effects, and you can estimate the coefficients of interest, and then we can debate whether they are the coefficients of interest, but we can estimate the betas without ever having to make assumptions about an additive individual specific effect, because we can difference it out. Okay? And we can do this from a panel with a finite number of time periods. Okay? We don't have to do stuff like Ivan did, where we assume that both n and t go to infinity. So the name of the game in the literature that I'll be talking about here is you have some model, YIT, you have a panel YIT, has some distribution that depends on some parameters. So YIT, so Y in time period T for individual I, depends on the explanatory variables for individual I, and maybe on past values of Y, and on an unobserved heterogeneity term, which I'll refer to as a fixed effect, but just think of it as unobserved heterogeneity. And then there's a vector parameters theta, and that's the vector parameters of interest, right? And in some of this literature, we specify a model for Y in time period T conditional only on explanatory variables up to time period T, and sometimes we assume that X is strictly exogenous, so we condition on all the T's, okay? So this is kind of, and again, kind of the question is, what can we say about the parameters of the model theta in a model like this for given functional form F? Okay? And I want to emphasize here that this is kind of a complement to the literature that Ivan was talking about, because here I have in mind settings where you have a short panel and with many observations. So like, if you look at, so those of you who don't know, I'm from Denmark, right? And a lot of people use register data. You have hundreds of thousands of observations observed over a few years, over relatively short number of years. So it seems like the relevant asymptotics should be n is big, t is small, so I'll focus on the case where t is fixed, n goes to infinity when I think about identification and when I think about estimation. Okay? I will take what's sometimes referred to as a fixed effects approach, in that I will make no assumptions on the relationship between the individual specific effect, the unobserved heterogeneity alpha, and the explanatory variables x. Okay, so, okay. Now, as you know, as many of you know, one problem with that is that in this model here, even if you know theta, even if you can manage to estimate or identify theta, that doesn't mean that you can identify counterfactuals, because counterfactuals will depend on the unobserved heterogeneity alpha. And since I only have a finite number of observations for each individual, I have no hope of backing out an alpha for each individual. So identifying theta doesn't necessarily tell you everything you want to know. If you have a structural model, it might do that. You might be interested in testing whether theta is equal to 0 or something like that. And then being able to identify theta is exactly what you want. But if you wanted to do like counterfactuals or something like that, then you'd also want to say something about the distribution of the alphas. I won't really talk about that, but it's not in the models I talk about. Once you've identified the parameters of interest, or maybe bounded them, it's not so hard to come up with bounds for counterfactuals. Okay? I just won't talk about that. All right. So here's the simplest case, and this is the classic case. This is, suppose you have a logit. So in time period t, you have a 0, 1 variable. In time period t, whether or not you observe a 0 or 1 depend on the x's in time period t. The coefficients are beta. And then in addition to beta, you have this unobserved heterogeneity alpha. And so this, if this wasn't here, this would just be a logit, right? So this is like kind of you take a linear regression model and you put in fixed effects by adding them to the x beta. That's exactly what I do here. Okay? And Rush, this is no old paper, Rush observed that in this model here, and here we're conditional on all the x's in all of the time periods. Okay? So x's are strictly exogenous. Rush observed that in this model here, if you write out the distribution of yi1 up to yit conditional on the x's and conditional on the sum of the y's, then that distribution does not depend on the individual specific effect alpha, but it does depend on beta. That's another way of saying that is that this is a sufficient statistic for alpha. So this distribution, the distribution of the data conditional on this, depends on beta. So we can write down the conditional likelihood, and we can use that to estimate beta. Okay? So this is kind of nice. So here, everything is just beautiful. It works. This line of argument here is the line of argument that if you write down the distribution conditional on the x's, it does not, conditional on the x's and on the sum of the y's, that distribution does not depend on the unobserved heterogeneity term alpha. That observation is specific to the logit. Okay? And as a matter of fact, it's clear, right, when I write down the conditional likelihood function here, it will have all, it's been proved, but it's kind of intuitively obvious that that will have all the usual properties of maximum likelihood estimators, will be root n consistent. But Chamberlain has a paper where he shows that actually the logit is the only model for which it is possible to get a root n consistent estimator of beta, subject to very weak regularity conditions. Okay? So in that sense, it is specific to the logit. On the other hand, Mansky has a paper where he showed that even without the logistic assumption, you can still identify beta, and you can construct a consistent estimator of beta. It's just not going to be root n consistent. Okay, so depending on, glass is half empty, half full, right? Either this is very specific to the logit or it's not specific to the logit at all, depending on a little bit what you talk about. Okay, now, you will note that this is references from like 1960, so you might say, well, this is awfully old-fashioned, and maybe this is something nobody cares about anymore, and why am I sitting here listening to this? So I just wanted to point out that there was a session here yesterday on network and panel data, and there are 4 papers, and 3 of the 4 papers really had this as its core, like kind of like where it all came from. And one of the 4 papers very explicitly, the paper by Chris and Irene, very explicitly used this, either this line of argument here, in a much more interesting, complicated setting, but either use this or the approach that Mansky suggested for the case where it's not a logit. Right? Also, there's a recent paper by Akapaveria, Gu, and Liu, where they are interested in kind of dynamic structural models of the type that people use, some people with I/O use. And they don't literally use the kind of models we have here, but they use the same kind of conditioning techniques that are used here and that I'll use on the next slides. Okay, so this is, even though some of the reference that I'll give you are very old, the type of stuff that I'm talking about is the same type of stuff that people are doing now. Okay, so, all right. So this all looks good, right? So this is great. We know how to do this. Here's something else that looks great, right? I mean, so you look at this model here and you say, well, here the x's have to be strictly exogenous. That doesn't, when you have data served over time, maybe you want to allow for some dynamics. So let's put in a lag-dependent variable here. So suppose the x was a lag-dependent variable. It turns out that in that case, it's also possible to find a sufficient statistic for alpha. It's the first observation, the sum of the observations, and the last observation for a given individual. That's a sufficient statistic for alpha. So if you write down the conditional distribution of the data for a given individual, conditional on that, that distribution will not depend on alpha, but it will depend on gamma, at least for some sequences of the y's, and so you can use that to estimate gamma. Okay? So that's all great, and this is actually goes back to an even older paper by Cox from '58. So this is all great. Okay. Now, right. So here you say, well, so now it seems like we know everything, right? It seems like we know everything. We know how to deal with the x's here. We know how to deal with a lag. So let's take one more example. So these are the 2 most simplest examples. The first and the second. Let's look at the third simplest example. That would be to have 2 lags. All right, so here we have 2 lags. It turns out again that if you write down the distribution of, and I'll just say it slowly here. If you write down the distribution of the data for individual I, and if you have 6 or more time periods, and you write down the distribution of the y's, conditional on the sum of the y's, conditional on the first 2 and the last 2 observations, the sum of the y's, and the sum of y times the lagged y. Okay? It turns out it's not difficult to write out. It's just really messy, but nothing hard. It turns out that that distribution depends on gamma 2, but it does not depend on alpha. It also does not depend on gamma 1, which you can think of as good news because it means that we can identify gamma 2 without ever making any assumptions about gamma 1. In particular, gamma 1 can be individual specific. Okay? So this also sounds great. Like, it sounds like I'm just going, this works, everything works, right? But the problem is here, there's a lot we don't know, and this is kind of what I want to start talking about. There's a lot we don't know. Okay? So for example, in this simple model here, right, as far as I know, okay, let me be clear. In this simple model, just as an econometric exercise to try to gain some insight, it would be nice to know how would you go about estimating gamma 1. Suppose we thought that this was the same for all observations, how would you go about estimating it? Now, I'm not going to claim that this is economically interesting. I think it is actually not. But I think it's related to a bunch of things that are economically interesting, but more complicated. And therefore, that's why I want to think about, if I can't understand this, then I can't understand something more complicated, right? So that's kind of that's the motivation, okay? And as far as I know, there's in this model here, nobody knows how to estimate this gamma here because all the conditioning arguments the only conditioning argument that we know to eliminate alpha also eliminates this gamma here. So the question is, how would you think about that? And so here's one strategy that, just to try to gain some insight, is just to try to numerically try to calculate in a given setting, do we think gamma 1 is identified, or do we think it is not identified? Okay? So the way I'm going to do this numerically is I'm going to assume a data generating process. Okay? Then on my computer, I'm going to calculate all the choice probabilities associated with that data generating process, right? If you have a binary choice model and you have 6 time periods, then there are 2 to the 6 different sequences you observe. We can calculate the probability of each of them given our data generating process. Then I'm going to say, well, some of the parameters of the model we can identify, like if you have 6 time periods, then we know gamma 2 is identified, so we can consider that known. So I'll consider that known. And then what I'm going to do is I'm going to try a bunch of values for the unidentified parameter. For each value, so in this case, for each value of gamma, I'm going to try to see whether I can find a distribution of the alphas such that my model gives me the same probabilities as the true probabilities, right? And if I have a gamma for which that's true, for which I can find a distribution of alpha that works, then that could be the true gamma. And so that could be the true gamma. If not, then I know I don't have the true gamma. And so the model would be identified if that gives me a unique gamma 1, okay? Okay, what we do, there's a little bit of complication here, right? Which is, I'll just put it in, it's trivial, but if I don't say it, then something else will become really confusing later, right? It's clear here that since we have 2 lags, we can't use the first 2 time periods, right? Because for those we don't have the lags. So we need to condition on those, but once you condition of those, then the distribution of alpha really becomes the distribution of alpha conditional on the first 2 values. So when I say we need to find a distribution for alpha, I really have in mind we need to find 4 distributions of alpha, 1 for each combination of the first 2 outcomes, right? Okay? All right. So in a paper with Katerina Kirisidou, we did this just because we were wondering, what could you say about gamma here, and we couldn't prove identification, we couldn't prove that it was not identified. What can you figure out? And we know, go back here, we know that gamma 2 is identified with 6 time periods. So the question is, what could you say? Okay, so here is what we did. So first we looked at 4 time periods. We made some assumptions about what the true gamma 1 and gamma 2 is. We've tried a whole bunch of different ones. I'm just showing you one here. And as you'd expect, gamma, with 4 time periods, neither gamma 1 nor gamma 2 is point identified. Right? Then we tried with 5 time periods. And again, when you think about this model, there are 2 lags, so you can kind of think about all the sequences that start with 0, 0, all the sequences that start with 1, 0, all the sequences start with 0, 1, or 1, 1, so there are 4 different ones. And what we find is that these are for different combinations there are many tables like this, but for different combinations of the parameters, what we find is that with 5 time periods, when we search numerically over the range of gamma 1 and gamma 2, gamma 1, from the sequence that start with 0, 0, with 5 time periods, gamma 1, 1, numerically anyway, looks a lot like it's point identified, in the sense that up to the number of digits that I present here, I can reject all other values of gamma given my data generating process. Right? For gamma 2, for conditional on the first 2 sequences, clearly I don't have identification, but it does look like I have identification if I condition on a 0, 1, 0, or 0, 1 in the first 2 periods. So it looks numerically here like either these gammas are point identified, but we don't know it, we just haven't been able to prove it yet, or the identified set is just so incredibly teeny that we can't see it. Okay? Honestly, so until like at lunch today, I was going to say, so I think, I was going to say, it's probably identified, we just don't know how to do it. Now I'm kind of going the other way and I'm saying, no, because I mean, at the end of the day, right, if you condition on the first two, and there are only 4, and there are 5 observations, if you condition on the first two, then there are only 8 possible sequences. Probabilities have had to add up, so there are really only 7 sequences, right? And certainly, I'm convinced that there's no conditioning argument, no conditioning likelihood argument that you can use to try to identify gamma, because there are only 7 different sequences here, and you can only try, there's a finite number of combinations of conditioning you can do, and I think we've tried them all, though not systematically. So this is what I said. This is kind of a puzzle, right? That these identified region, either these are identified and we don't know it, but then my feeling is that if they are, then the argument has to be different from a conditioning likelihood point of view. But in this simple model where there's only lagged y's, I don't know what we have other than the conditional distribution, conditioning arguments. I don't know what we have. Okay, so this is kind of a puzzle, and I'm just going to leave it up there if people have good ideas. Good. Okay, so this is clearly a toy model, but it's still kind of, it's a clear toy model, but the point is, right, I mean, the toy models are exactly the models where we should be able to say something, and then when we get something that's empirically relevant, then things get messy. But here, things are messy even in the toy model, right? So that's, okay. All right. Okay, so to turn to something, just to be positive for a minute and say something we do know, so, so it's not all kind of like just confusing, so something we do know. So we also looked at, right, so there's a lot of literature, modern literature, on having like bivariate having bivariate binary outcomes where they depend on each other, like entry games and so on. That will be the next slide. But there's also an old literature where people try to look at 2 binary outcomes and want to allow for the possibility that they're related to each other. So in particular, there's a paper by Smith and Strauss where they said, suppose we have 2 binary outcomes for a given individual. Right, it could be whether you're 2 different outcomes, right? Whether you're married and smoking or whatever, right? And you might think that they depend on each other. They're correlated with each other somehow. Suppose we said we want the distribution of y1 conditional on y2 to be a logit, and we want the distribution of y1 conditional of y2 conditional on y1 to be a logit, then you can reverse engineer a joint distribution of y1 and y2 for which that's true, right? So they did that in just a regular cross-section case. We took exactly what they did, and we put in fixed effects, okay, just as a little exercise, because we thought it would be kind of interesting to think, mostly because of what comes next, but in terms of history of econometrics, this is kind of first, right? So we just put in fixed effects here, and we showed that, in the paper with Katerina, we showed that in this model here, you can actually identify beta 1 and beta 2 and rho with 2 time periods. There's a conditioning argument. It's boring. It's tedious to write down, but there's a conditioning argument that says conditional on something, I can get a probability statement that depends on beta 1 and beta 2 and rho, and I can use that probability statement to estimate, but does not depend on the fixed effects alpha 1 and alpha 2, and I can use that to estimate beta 1, beta 2, and rho. All right, so that's good. As I said, this is really, this is clearly an old paper, and clearly I didn't really give you any motivation for wanting to say that conditional on y1, y2 is a logit and vice versa. I just said because, but I didn't, right? But I didn't tell you why, right? So, in kind of a more modern setup, right, a lot of people have looked at entry games where, so in a in a stylized model, you would have, there are two firms entering a market. Whether firm 1 enters depends on whether firm 2 has entered and vice versa. So you're looking for a Nash equilibrium. And so the model is something like this, where if Y2 enters, this is the decision for Y1, and this is for Y2. And then you're looking for a Nash equilibrium here, and then if I have a negative sign on here to remind you that if gamma then is positive, if this coefficient is negative, so gamma is positive, then this is an incomplete econometric model, and so we know that you cannot write down a likelihood function. But in a cross-section, people have then figured out how to estimate this model just nonetheless. Okay? So what in a kind of work that I'm doing right now, we have some results, but we're still working on it. With Honoré de Paula, we're looking at models like this, but in a panel data setting. So in the simplest case, we're just going to take the Bresnahan-Rees, people refer to Bresnahan-Rees for like entry games, right? Just take this model here and put in individual specific fixed effect alpha 1 and alpha 2. Okay? And then we ask ourselves, what can you say about beta? And in some of what we do, we assume that the epsilons are logistic, so we have logits. But for what I want to say here, that actually doesn't matter. It shows up on the slides just because it leads into something else that I'm not going to talk about. So, right? Okay? Just because, okay? So again, you might wonder, well, is this something I am making up? And I'm going to say, no, it's not. This is established literature in I/O. But even like yesterday, there was a session on social interactions yesterday afternoon, and one of the papers was looking at whether a household is likely to participate or take advantage of the social program in Chile. And the question was, to what extent do your neighbors have an effect on that? And so the idea was they looked at people who lived in the same apartment building. And for my purpose, let's just assume there are only 2 families live in an apartment building. Right? Then the idea is that they may have a spillover from one to each other. Now, they estimated linear probability models. So Y1 depends on Y2, and Y2 depends on Y1, and talked about it like that. But if you wanted to think about it, these are 0 or 1 variables. They are. Right? This would be exactly either this, if you wanted to think about like, so in that case, right, the coefficient on Y2 presumably be positive, so you would not have an incomplete econometric model. You would actually have a complete econometric model. The idea being that if my neighbor participates in this program, then there's less stigma for me to do it. Right? So, but the point is that this type of models here, and even this type of models here, it is exact. I mean, this is exactly the kind of stuff that people are doing, at least in some literature. Right? So, okay. So the question is, in this model here, what can we say? And I'm just going to give you 2 results, and then I'm going to tell you something I don't know. So the 2 things I know is that if the x's are market-specific, so think about this as just 2 firms entering a market, right? So stylized I/O model, 2 firms enter a market. Their explanatory variables x, and then there's this interaction between the 2. If the x's are market-level variables, so there are things that affect both firms equally in every time period, but changes from time to time. Because when gamma is positive, this is an incomplete econometric model, I cannot look at the likelihood function. But I can ask myself, what is the probability that both firms enter the market? The probability that both firms enter the market, I can write that out. Here I've used the logit form, but it actually doesn't matter. Right? It has this form here. This is in time period 1, this is in time period 2. And clearly, the probability that, so just look at them. So this is just the x's are the same for the 2 firms because the x's are market specific. Clearly, the probability that there are 2 firms in time period 1 is bigger than the probability that 2 firms in time period 2 if x1 beta is bigger than x2 beta. So in this model, you can use like maximum score kind of arguments to identify beta without making assumptions about these market-specific fixed effects, firm-specific fixed effects. okay? Okay, and it doesn't matter that this is a logit, as long as it's a CDF, which it will be, so it's monotone, that argument is true. It's, okay, okay. You can also, right, there are a whole bunch of cases that we consider, we're just working on it now, right? So this case, so here we know you do this, and now you can identify beta just from comparing, is this probability greater than this probability? So you can do like a maximum score argument to identify beta. That works. You can also, if the x's are not market specific, you can also condition, kind of doing conditioning arguments, so that implicitly assumes some support conditions about the, some assumptions in support of the x's. But suppose we condition on player 2 having the same x in 2 time periods, then again we can ask what is the probability that again, we can ask what is the probability that there are two firms entering in a given time period. It has this form here where F is the joint distribution of the 2 epsilons. And now for this slide, I'm just pointing out explicitly that you don't have to use the logistic. Right? And again, you see that the probability is higher in time period 1 than in time period 2, depending on whether this is greater than this. And again, you can use a maximum score conditional on the x's being the same for player number 2. Right? So again, you can identify beta in a model like this. Okay? So, but again, we don't know anything about gamma. We don't know anything about gamma. We cannot, the conditioning arguments that we have tried, none of them allow us to point identify gamma, and we think it is not point identified. And so again, we're trying to work on trying to do this numerically to see what you get out of it. Okay, now, one little observation here. Now, I'll skip this. In this paper, okay, when we do this thing numerically, right, we say, well, we're going to search over the distribution for the fixed effects, and then what we do in practice is we approximate the distribution of the fixed effects by a discrete distribution. Okay? That's the way what I did with Katarina, that's the way we thought about it. Now, in the paper with Aureo, we actually show that there is no loss of generality in doing that as long as you allow the point of support to be unknown, okay? And for some, you only need a small number of points of support of unknown points of support. We haven't written that up yet because we kind of think that we can get to the point where we can say, actually tell you, you just need these points of support, and then with these points of support, there's no loss of generality, okay, in terms of proving identification. So anyway, we're working on that. Okay, good. All right. Good. Once you start talking about having 2 Y's in a panel, it becomes again natural to think about having lags in there, right? Just because if you have a panel, you think there's some dynamics going on. So the, right? I mean, to some extent, that's one big reason why panel data is interesting, is to think about dynamics. So again, so people historically have thought about like a bivariate model where you have as explanatory variables the lag of 2 Y's, and again, consider logit, and this paper here shows that with 4 time periods, you can come up with a conditional argument that identifies all the gammas. So that's great. Now, in this model here, it is, you might say, it's a little bit funny to have, this is like a vector autoregression in a discrete choice, right? You might say in this vector autoregression, it's a little bit funny to assume that these shocks here are independent of each other, right? If I think that y1 and y2, they're dependent on each other's past values, it seems like in most empirical applications, you would like to then allow for some correlation in the epsilons. So one way to think about that is, what we did was we said, well, let's just take this model here, but then combine that with the Strauss-Smith model, where you're allowing y1 to depend on y2, and vice versa contemporaneously. So that gives us a, right, so you get a model like this. And then when rho is equal to 0, we're back to this model here, and rho then captures like the correlation between the epsilons, essentially. All right? It turns out that in this model here, again, we can point identify the gammas, but by conditioning argument, but all the conditioning arguments that we have come up with, they all, once you condition to eliminate the individual specific effect, this rho term here also drops out. Right? That was not true. Oops, sorry. That was not true in the static case. In the static case, the conditioning arguments that we came up with left rho in there, and we could identify it. But in the dynamic case, it seems like no matter what you do, this rho term there drops out. So again, to try to gain insights about whether rho is identified, and again, I don't want you to leave here thinking that this is a super interesting model in itself. I want you to leave thing here saying, even in this super simple model, which is closely related to something that I might care about, even in that super simple model, identification is really tricky and we don't really know what to do. Okay? So I'm going to skip these because it's not new anyway. No. So again, to check, to try to get an idea about whether rho is identified, is point identified, what we do is we ask, okay, we can identify the other parameters. So in a given setting, we can pretend we know the other parameters. And then we can say for a given data generating process, search over a bunch of different values for rho and ask, is there a distribution of the alphas that will give us, such that our models will give us the same thing as the data generating process? And if the answer is yes, then that rho could be the true value of rho. Okay? So what I'm plotting here, it is not quite true, but it is almost true. What I'm plotting here is as a function of rho, how close can I make the model probabilities to the actual probabilities that I have when I use the true rho? Okay? So I'm minimizing over, so for given value of, for given guess of rho, I'm minimizing the distance between the sample probabilities and the theoretical probabilities. Okay? And at the true rho, those should be equal to each other. And at any other rho that will make them equal, that could be the true rho. Okay? Here again, since it's the dynamic model, and there are two y's, and we have to worry about the initial conditions. There are 4 possibilities for the initial conditions. So we can ask that question conditional on the first being a 0, 0, a 0, 1, a 1, 0, da, da. So there are 4 functions. So what I'm plotting here is essentially the distance between, the sum of the distance between the model probabilities and the sample probabilities. In this particular numerical example, the true parameter is 0.7. And we see that with 3 time periods, there's a range of rhos that will make it equal to 0. So even if we knew the gammas, we wouldn't be able to nail down rho. Okay? But here it is for 4. Right? This is the case. We don't know theoretical whether rho is point identified or not. But when I plot, this is how, when I plot this function here, which is how close can I make the model probabilities to the actual sample probabilities, it seems like the true 0.7 is really the only number that works here, right? So it looks like from this graph here, it looks like rho is point identified, but we don't know it. Okay? So I just want to tell you, so all of this was kind of theoretical stuff, and it was all kind of toy model stuff. So what I want to do now is to say, and hopefully at least some people say, well, this is related to some stuff you might want to do, but except what I want to do is actually more complicated, so if I can't, so it's kind of informative that it's so hard here, right? But I want to make another point, which is that these conditional tricks that I talked about can actually be useful in completely different contexts, okay? And I'll try to do this very quickly. So this is stuff that I have just begun with a person in Denmark. Okay, so in Denmark there's kind of a set of politicians who are obsessed with the idea of moving stuff from Copenhagen out. You know, they don't want everything to be concentrated in Copenhagen. And we can have political thoughts about that, but it's true. These people exist. And there are a lot of policies aimed at getting people out, to move out to where nobody else is living. Okay? And one of the policies is to establish educations, like studying to be a nurse or something like that. Establish those educations out in the country, and then hopefully you get people to move there, and then that will lead people to live there in the long run once they move there. Okay? Now, of course, to evaluate this, you somehow need to come up, you like to evaluate this, and so you would like to come up with a model for saying, well, what is the effect of somebody studying in a place on her actually living in that place in the long run? Okay? So, because the idea is you want to establish these educations because we want people to move there and stay there and this be a vibrant community and so on. All right? Okay. So we want to try to write down a simple structural model to try to estimate that and try to come up with some counterfactuals. Everything is parametric. There's no fixed effect in sight here. Okay? Of course, the problem is that people don't randomly choose what education to get. And in particular, you think that if I really have a preference for living in a particular part of Denmark, in the long run, that's probably correlated to me also wanting to study in this place. So you don't want to consider where you study exogenous when you think about where people live in the long run. All right, good. So that means that as part of this, we need to come up with a model for what course of study people choose. Okay? And so I'll just tell you, right, so you have many, many different choices. The way it works in Denmark is when people apply to universities to other courses of study, you rank up to 8 choices, and then you get in. And then there's a cutoff in terms of GPA, and then you get in, into the highest ranked one where you satisfy the requirements. Okay, okay. So what we do is we set up a little model where we say for all these different programs, it's like a random utility model. There's an error term. Part of the error term is that, of course, we don't think that the errors are all uncorrelated with, of course, all studies, right? You might think that some people have a preference for studying the sciences. So there's like a random effect for subject. And then there's also a random effect for location. Some people would like to be in Aarhus or in Aalborg or whatever, right? So there's also a random effect for location. So in principle, so this is a completely parametric model. In principle, you can write down a likelihood function. It's incredibly complicated. Nobody would ever want to do that, no matter how ambitious you are. You could also do method of simulated moments. It's easier to simulate from the model. But getting that to converge, I would try. It's just very hard. There are many, many parameters. It's very complicated. Right? But what I want to show is, since these individuals can rank 8 choices, we can do stuff like, suppose you have 2 programs. Suppose a student ranks 4 programs, and 2 of them share the same location and the same subject matter, like natural sciences. And the other 2 also share location and subject, but different location and subjects. Then we can ask ourselves, what is the probability that the individual ranks program 1 above program 3 in the ranking, and the same for 2 and 4? Right. There's a little bit of math here because the conditional is a little bit funny, but it has this form here. Don't worry about it. But the point is that when you look at this, these random effects for location and for program, when I look at this probability compared to this probability, they are the same. So from a mathematical point of view, I can think about this as if it was a fixed effect. I don't have to, because I'm willing to make distribution assumptions on it, but I can. But then if I'm willing to do that, and if I'm willing to assume that this guy here is logistic, now I can treat these as fixed effects, and now I can use the Rush conditioning argument to estimate a whole bunch of the parameters in a very, very simple form. So the point about this is that I can use these conditioning arguments that are so prevalent in the fixed effects literature. I can use those tricks, those conditioning arguments, to do something in a completely different context. I can do it, I can use those arguments to estimate a whole bunch of parameters easily, and then I can focus on, then there's some parameters left that I'll have to write down a likelihood function or method of moments or whatever for the rest. All right. All right. So what's the conclusion here? The conclusion is that in these very simple models, there are some parameters where we don't know if they're point identified, but it looks like they are numerically. And that's the puzzle part, and that's, in some sense, that's the most exciting because it's something we don't know. It seems like, and it's so simple, right? I mean, you have, in these, we have like 7 probabilities, I think, we should be able to work this out. But we have not been able to. And it seems like these conditioning arguments that we're used to using don't work, so we have to either come up with a new identification strategy or try to prove that the parameters are not identified, okay? And in particular, Chamberlain has a paper for the static logit where under some conditions on the explanatory variables, he shows that the logit model is the only model for which the parameter is identified. That contradicts a little bit what I said about Mansky, but it's just that they're making different assumptions, so there's no contradiction. Okay? And so I have started doing some of that stuff with Katerina Kiyosidu where we say, well, gee, we have these parameters. It looks like they're identified, but we don't know. We have not been able to prove that they are, so let's try to prove that they are not. Right? And we have a little bit of progress in just the simple case where you have an AR1 model. That was a model, just one lag. And where we think that it is only point identified if you have a logit. We haven't quite been able to prove that. But what we have been able to prove is that at a given point, we think we proved it. But it's not at a given point, you have to be within a 4-parameter family of distributions, but then since there's always a location and a scale normalization, we're really down to 2 parameters. A 2-parameter family of distributions that works at that gamma, but then if you want identification across all gammas, we hope that we can narrow it down to saying it is only identified at the logit. And then the idea is that maybe by doing those kind of arguments, which unfortunately, if you read Chamberlain's paper, it's very elegant, but once you try to generalize it, it gets very, very complicated, very, very messy. Use those kind of arguments to try to argue that actually these parameters that look like they're point identified actually are not. And the problem is, in the meantime, we're kind of stuck not knowing, and that's annoying, right? So we either we would like to prove that they are identified or prove that they're not, and then at least we know. Okay. Going back, last thing I'll say, and then I'll be out of time. Last thing I'll say is that these dynamic models that I wrote down, they're very mechanical, right? They're y in time period t depends on y in time period t minus 1. So it's like as if there's some machine that generates the y's in this way. If these were choices of individuals, then you would like to think that an individual will take into account that the choice I make today will have an effect on me because of the dynamics. My choice today will have an effect tomorrow, because tomorrow my lag y will matter. So if you try to make this into like a utility put this into a utility maximizing context, so this does not fit a utility maximizing context from that point of view. There is a paper by Gu and Liu that do that. There's like a continuation value in the x beta part. It doesn't, and clearly, if we're starting working on this paper, if Katerina Kiyosidu and I were starting working on this paper now, we would have done that kind of stuff. All the issues are the same, but it becomes much more interesting from an economic point of view, and it becomes like much more something where you would say, well, this fits naturally into a dynamic discrete choice model in like a John Rust kind of way. And so anyway, sorry I went over.